Hello everyone, this is Karthik Gopalan for CS350. In this lecture, we are going to discuss paging and page replacement algorithms. This is a continuation of the topic of memory management. All the material is from section 3.4 of Andrew Tenenbaum's Modern Operating Systems. So first, let's take a look at the various times at which the operating system handles page tables. There are four distinct instances where the operating system may manipulate page tables. First is when the process is created by the operating system. At this time, the operating system has to create the page tables for a new process. Then every time the process is switched on to the CPU, whenever there is a context switch, then the operating system has to load the memory management unit or MMU with the location of the new page table. So this involves setting the page table base register to the location of the new page table. In addition, the TLB may also be flushed. On some architectures, the TLB may be flushed. On others, if it's a tag TLB, the TLB may not be flushed. The third instance is at the page fault time. We will discuss what exactly is a page fault, but essentially whenever a page fault occurs, then the operating system has to handle the page fault. So um, and finally, when a process dies, then operating system has to release all the page table memory. So let's see what exactly is a page fault. Page fault is an exception generated by the CPU execution hardware. Whenever a process accesses a virtual memory address for which a physical page is not yet allocated, then the hardware raises a page fault, meaning that the hardware was not able to find access the physical page associated with that address. So at this point, the operating system has to figure out how to resolve the page fault. So a page fault can occur when either the page has been allocated but it's not currently resident in the main memory. The page may be resident on the hard disk. Secondly, page fault can also occur if a process accesses a page for which it doesn't have the appropriate permission. For example, if a page accesses a read only page and tries to write to that page. So, so this would generate a hardware exception which is identical to a page fault. Finally, if a page has not yet been allocated by the operating system, if the memory location is being accessed for the very first time, then again a page fault would be generated, and this needs to be handled by the operating system. So the page fault handling is performed in software by the operating system. Whenever a page fault exception occurs, a specific routine or page fault handling routine is triggered in the operating system. The various steps taken by the page fault handling routine are described in this slide. So, uh, so first the MMU would raise a trap. Once the process accesses the virtual address, the MMU would raise the trap, and then the first thing that this trap does is that the process is paused. Whatever it is doing is stopped. The state of the process is saved. Its program counter registers. Everything is saved somewhere by the operating system, and then the operating system jumps to a page fault handling routine, basically a function in the operating system that knows how to handle the page fault. So so this is the step 4 is the most involved step. The job of the page fault handler is to examine the virtual address which caused the page fault. So the virtual address which caused the page fault is usually stored in the CR2 register, so at least in the Intel architecture. So once the page fault handler examines the virtual address, it has to check what type of allocation is this, what type of access is it. If this is a write operation to an unallocated page, then the page fault handler would go ahead and allocate a new physical page. And once the physical page is allocated, then the process would be allowed to continue. If the page fault occurred on an address for which a page was already allocated, then it means that the page is sitting on the hard disk. It's not present in the main memory. So the page fault handler would read the page from the swap device, and once the page has been brought back into the main memory, the handler would update the page table of the process. So the page table has to be updated to reflect the fact that now you have the page resident in the main memory. So and finally, if the third reason why, if the virtual address access was disallowed, then the page fault handler may inform the operating system, and operating system would terminate the process. So the page fault handler is responsible for handling all of these three conditions: write to an unallocated page, or accessing an allocated page which is non-resident, or accessing a page in a manner which is disallowed. So once the page fault handler has finished its processing, if the process is still alive, then it would continue executing from wherever it left off. Basically, the program counter and registers that we had saved earlier in step 3, they would be restored in step 5, and then the process would be allowed to continue. So there is one additional topic you may want to know about, which is that in some instances, uh, page out of certain pages may be disallowed by the operating system. So usually the reason for this is related to memory mapped I/O operations. Sometimes I/O devices they have direct access to certain physical memory pages to perform I/O operations. So the virtual memory subsystem may lock these pages in memory. Locking pages in memory means that the operating system would mark these pages as not being swapped out. So these pages would never be selected as victim pages whenever the operating system has to pick a victim page. So this way you don't have a situation where when an IO device accesses a piece of memory, that memory page has been swapped out. So because then otherwise it would lead to incorrect IO operations. So now this brings us to the main topic of this lecture, which is page replacement algorithms. So page replacement algorithm means that as sometimes operating system has to decide to kick out some pages from the main memory so that it can make space for new pages to come into the memory. So a critical component of page replacement is deciding which pages should be evicted from the main memory. There can be various policies for evicting pages from main memory, and in this lecture we will look at some of these policies. Whatever the policy may be, there are certain things that are common with all the page replacement algorithms. So if whenever a page is being evicted, the operating system will examine the page. If it is found that the page has not been modified since it was brought into the main memory, then the OS can choose to simply discard the page. But discarding means that you can simply reuse that page for some other process. So for example, allocating memory to another process. Um, so the point is that we don't have to write clean pages to the disk. We don't have to page out clean pages. If a page was never modified, there is no reason to write it to the disk, because there was likely already a copy of the exact same page in the disk. If the page was modified since it was last brought into the main memory, then at this point we have some updated contents in the page. So these have to be saved to the disk before the page is reused. So modified pages are also known as dirty pages, and dirty pages have to be saved to the disk before their corresponding physical page can be reused. And uh, most of the page replacement algorithms, they have a very common goal, which is to minimize the number of page faults. um, so this is a very clear metric. Unlike CPU scheduling algorithms where you can have different types of metrics, or page replacement algorithms, the metric is pretty straightforward, minimizing the number of page faults. So to see an example of why uh, the algorithm can have an impact on the page faults, assume that your algorithm replaces a page that's being used very often. Then the moment the page is evicted from the main memory, some part of the system, some process, or even the operating system itself may ask for the page again, may try to access the page. So in which case the page has to be brought back in. So if you evict frequently accessed pages, then those pages would come right back into the main memory. So this situation is called thrashing, where a page is repeatedly coming in and out of the memory, and this would result in a large number of page faults. So the common goal of page replacement algorithms is to identify pages that are least needed and then to evict only those pages. Of course, this is easier said than done for various reasons that we will discuss in the rest of this lecture. So there are a number of different page replacement algorithms that are available in literature, and some of them work better than others. So we will start with the ideal algorithm, optimal page replacement, and then we will go through the rest of these algorithms one at a time. So the optimal page replacement algorithm works as follows. Its goal is to replace a page that will not be needed for the longest time in the future. So assume that you have an oracle, or a crystal ball that tells you what will be the page accesses for a program all the way into the future to its termination. So if you knew all the future page accesses, all the addresses of every page that will be accessed by the program, then you can find the page that will not be needed for the longest time, and pick that page as the victim. So an example is given here. The green boxes, they represent the page access timeline. First, page 1 is accessed by the program, then page 2, then 3, then 4, then 1 again, and 5, 2, and 4 respectively. Um, so the page replacement algorithm works as follows. You have three physical pages. We call them frame 0, frame 1, and frame 2. Initially, all the three frames are empty. So when page 1 is accessed, there is a page fault, and the page is brought into the main memory because we had an empty slot. Then when 2 is accessed, 2 is brought in. When 3 is accessed, 3 is brought into the main memory. Finally, we run out of physical memory slots. So when page 4 is accessed at time t3, we have to select one of the pages as victim pages, one of the pages 1, 2, and 3 as victim pages. So we look into the future. After page access 4, we see which page will not be needed for the longest time among 1, 2, and 3. So we see that 1 is needed at time t4 and 2 is needed at time t6, whereas page 3 is not being accessed for the rest of the process lifetime. So we choose page 3 as the victim. So 3 is evicted and 4 is brought into the main memory. Now at time t4, page 1 is accessed again, and we don't have a page fault because 1 is already in the main memory. At t5, page 5 is accessed. So at this point we again look into the future, which page will not be accessed for the longest time. among 1, 2, and 4. So we see that 2 and 4 are accessed, whereas 1 will not be accessed again. So we evict page 1 and bring in page 5. And subsequently, when page 2 is accessed, there's no page fault, and then page 4 is accessed again, there's no page fault. So here we saw that by looking into the future page accesses, we were able to determine which page can be evicted. So of course this algorithm is called optimal for a reason, and we will look at the reasons why it's called optimal. So the optimal page replacement algorithm, it's called optimal because apparently no algorithm can give you fewer page faults than the optimal algorithm. Now this sounds really nice, so why don't we just use an optimal algorithm? Well, because you cannot implement the optimal algorithm. The OPR algorithm, it depends upon the knowledge of all the future memory accesses. Unfortunately, it is almost impossible to predict for any reasonably complex program. It's almost impossible to predict what will be all the future memory accesses for the program. So so all that the purpose of OPR is to give a baseline. Basically, if it tells you like what's the best that any algorithm can do. So if you design a page replacement algorithm, OPR can tell you what will be the minimum number of page faults that we can ever expect to achieve with a given set of memory accesses. So again, how do we know it's optimal? You can try proof by contradiction. You can assume there's another algorithm that does better than OPR, which doesn't pick the page that's accessed farthest point in the future. And then you can find a situation where you can um, pick another page which is accessed at the farthest point and show that it will lead to fewer number of page faults. So I'm skipping the formal proof of the algorithm here, of the optimality criteria here, but feel free to refer to the Andrew Tenenbaum's book for the proof. Uh, Other algorithms, they try to approximate the OPR algorithm. Because we cannot have perfect knowledge of the future, some algorithms have other means of predicting which pages will not be needed for the longest time. So we'll be looking at other algorithms now to see how they approximate OPR. So the most um, popular approximation for OPR is the least recently used algorithm, or LRU. Now, the basic idea is that if we don't know the future, we can predict the future by looking at the past, right? So much like how the stock market works, you don't know what the future stock prices will be, but you can predict which stocks will do better by looking at their past performance. Of course, you can be wrong. Sometimes past history is not a good predictor of the future. So, with least recently used, we look at pages which have not been used for the longest time in the past, and we assume that the same pages will not be used again in the future. So if we had a history of page accesses, if we keep a history of page accesses with their timestamps, then whenever we have to evict a page, we pick the page which hasn't been used for the longest time. So this again sounds very intuitive, except that there is a very fundamental problem with LRU. That just like with OPR, it's pretty hard to implement. I mean, it's not impossible to implement LRU, but it's pretty hard. Just think about what you need to do. Upon and every memory access, we have to first record that the corresponding page was accessed at that time, which means that for every page we must keep a timestamp, right? At every memory reference. Normally when a program runs, when a process is executing and it accesses memory, operating system is not involved in the memory access. The MMU directly accesses the memory and fetches the corresponding data or writes to that location. So operating system is not involved. But for LRU now, we would have to somehow record the timestamp for every page upon every memory access. That's a pretty hard requirement, especially if we don't want the operating system to get involved. So essentially what it means that there has to be a lot of hardware to keep track of the timestamp for every memory reference. Now this can get prohibitively expensive. Like past how much memory past history are we trying to keep track of? So there are various approximations for LRU that are so we can't add too much hardware. We cannot have operating system intervening upon every memory access. So as a result, people try to approximate LRU in various ways. One option is called aging, where we keep a counter associated with every page table entry, and then we add additional hardware wherein upon every memory access the counter is incremented in some manner. So, and when you have to evict a page, you pick the page with the smallest value of the counter. Now, so again, this seems like a fairly good approximation of LRU, except that you have to decide how many bits you want to allocate to the counter. This is again an extra overhead that the hardware will have to that will increase the hardware complexity. So I'll be skipping the specific details of this aging algorithm. These details are in section 3.4.7, which are very interesting details. But I'm going to stay focused on other algorithms that are more often used in modern operating systems. So before we move on to other algorithms that approximate LRU, let's just recall what a page table entry looks like. So in this picture, this is a typical page table entry that we had discussed earlier. There is the page frame number and the present absent bit, the protection bits. In addition, there are two specific bits we are interested in, the referenced and the modified bit. So the referenced bit is a single bit which is set whenever a page is accessed by any part of the software. So whether there is a read access or a write access to a page, the reference bit in the corresponding page table entry is set. The modified bit is set whenever a page process writes to a page. So it's also called a dirty bit. So what this means, if the dirty bit is set, then it means that since the last time the operating system examined this page table entry, the process has gone ahead and modified this page. So, um, so these two bits play a very important role. Of course, the present absent bit is also involved in the page replacement algorithm. So if the present bit is set to 1, then it means the page frame is valid. If the present bit is 0, then it means the page has been swapped out. So now let's take a look at how the referenced and the modified bits are used by various algorithms. So a very simple algorithm that approximates LRU is called not recently used algorithm, or NRU. So since we have two bits, referenced and modified, there are four possible combinations of these bits: 0, 0, 0, 1, 1, 0, and 1, 1. So what this means is that every page table entry falls into one of four categories. The first category is pages that have not been referenced and not been modified since the last time the operating system reset these bits. The second category is not referenced and modified. The third category is referenced and not modified, and the fourth category is referenced and modified. So the algorithm is very simple. When the operating system has to select a victim page, it would find the lowest numbered non-empty class. So it would start from class number 1 and if that class is not empty, then it would pick a page from that class. If class 1 is empty, then it would look at class 2 and pick a page from class 2. If class 2 is empty, it will go to 3 and then 4. So whenever it finds a non-empty class, it just picks any one page from the first non-empty class and evicts that page. When it does so, when it evicts a page, it also resets all referenced bits. So by resetting the reference bit, we are moving those pages up by up the class hierarchy. So what that means is that sorry, the pages are moved down the class hierarchy. So what that means is that if a page belonged to class 3, then by resetting the reference bit, it would move to class 1. And if it earlier belonged to class 4, then it would then move to class 2. So uh, so essentially the intuition behind the algorithm is that the lowest number class reference has pages that haven't been accessed for a while, and then we give preference to dirtied pages or non-dirtied pages when if provided their reference bits are the same. So so remember that NRU scans the page table entries periodically, say maybe every 1 second or every 10 seconds. So between each scan, the pages are accessed again, and their corresponding reference and dirty bits may change. So if a page is accessed again, the pages may again move up the hierarchy. So if a page was in class 1, it may move to class 3 if it's referenced, and to class 4 if it is modified. If it was in class 2, then it could move to class 4. If it was in class 3, it could move to class 4. So um, so pages again can move between NRU scans, and then the next NRU scan, the next victim page would be selected, and the reference bits would be reset. So the algorithm is really simple to implement. It just relies on 2 bits in the page table entry, um, and it's fairly intuitive, very easy to understand, right? But there is a big disadvantage. If you have a lot of pages in the system, there are only 4 categories, which means that every category can have a large number of pages. So within a single category, there is no distinction between various pages. So this algorithm doesn't really distinguish um, how to order or give priority to pages within the same class. So if we were to do that, then we would need to have additional complexity either in the hardware or the software. So so NRU is simple to implement, but then it's also too approximate, probably too approximate to be used in practice. So we'll look at some other algorithms that might be doing somewhat better than not recently used. So another algorithm, again, which is very intuitive, it's called FIFO, or first in, first out page replacement algorithm. As the name suggests, if a page was the earliest one to come into memory, then it would be the first one to be picked as the victim page. So pages are sorted in the order in which they come into the main memory. Usually some kind of a linked list is maintained of the order in which a pages came into the main memory. So if we have to select a victim page, we select the oldest page in the memory and kick it out. Okay. Again, it's simple, but there is one big disadvantage to first in, first out. It is that the oldest page in memory may also be the one which is being used most often. So if you're kicking out a page and it's being used often by the software or the process, um, then it may be a wrong victim page to select, because as soon as the page is kicked out, it will be accessed again and it will have to be brought back into the main memory. So this would defeat our goal of reducing the number of page faults. So the subsequent algorithm that we will discuss, it tries to improve upon first in, first out. In fact, the improvement is really simple. This is known as second chance page replacement algorithm. So second chance algorithm is just like first in, first out. It would pick the oldest page in memory as the victim. But before kicking the page out, it would give the page a second chance. Second chance means that it would examine the referenced bit for the page, the R bit. If the R bit is set, then the page will not be kicked out. It would be, in fact, be moved to the beginning of the FIFO list. It would be marked as the most recent page, and its reference bit will be set to 0. So its reference bit would be reset. So that's the second chance part of it. You give a page a second chance by examining its reference bit. If the reference bit set, it means the page was recently accessed, so you move it to the front of the list. Okay, so it's a very simple variant of first in, first out algorithm. If so once you give a page the second chance and you move it to the front of the list, you go to the next page in the list and examine the reference bit again, and so on till you find a page whose referenced bit is 0, and that page would be kicked out from the main memory. So it turns out second chance algorithm works really well. It's a pretty good approximation for LRU. Um, the only problem here is that we have to maintain a linked list, which means that there are quite a few, whenever you have a linked list, as you may be aware, there are quite a few memory references you have to do to move things around in a linked list. Here we are moving a page from the tail of the list to the head of the list. So there are quite a few memory accesses that need to be done to do this. So operating system designers, they don't like a lot of pointer references or memory accesses in critical path. Page replacement could be in the critical path, so we want to make this as simple as possible. So there is an implementation of second chance algorithm which we will discuss next, which is called the clock page replacement algorithm. Clock is identical to second chance algorithm. That's basically the second chance algorithm. The only difference is how you would implement it. So instead of moving pages around in a linked list, what we do is we arrange all the pages in a circular linked list, right? So by organizing them in a circular linked list or a circular array, for example, all you do is you keep a pointer called, which for us in this figure it represents the hand of a clock. All right, and only the hand of the clock means moves, only the pointer moves from one item to the next. So the algorithm works as follows: whenever a page fault occurs, and you have to find a victim page, the page to which that hand is pointing, it is inspected. If the R bit is 0, we evict the page. If the R bit is 1, then we reset the R bit to 0, and then we move the hand to the next item in the circular list. So as a result, we don't have to move items around in a linked list if we are giving a page a second chance. So it turns out that you need to make fewer memory accesses to implement the clock algorithm than to implement the second chance algorithm using a linked list. Otherwise, there is no difference between clock and second chance. They are basically the same algorithm, just that the data structures used and the way they are manipulated is different. So this brings us next to a very important concept uh, in in the page replacement algorithm. This is the notion of a working set. A working set refers to all the pages that are currently being used by the process. So if a process, let's say it has 4 gigabytes of virtual address space, right? Um, of all the allocated pages, let's say it's using only a fraction, maybe 100 MB of those pages. So all the other pages that have been allocated other than the 100 MB, they can be swapped out to the disk. As long as the 100 MB of actively used pages are in the main memory, the process would happily execute without any page faults. So the trick becomes, how do we identify the set of actively used pages and keep them in the main memory? So the set of actively used pages is known as the working set pages, and the other set of inactive pages that are not being used by the process, they are called cold pages, pages that the process doesn't need. So in theory, if you keep the working set in memory, then the process will not encounter any page faults. Okay. Of course, there is a problem that, one, you need to predict what is the working set for a process, and secondly, even if you could predict it, the working set keeps changing during the lifetime of a process. For example, a process may be working on one array at one point in time, then it may go on and work on another array at another point in time. So the working set changes, right? So your prediction algorithm should be able to predict the changes in the working set, not just one working set. So the graph here shows uh, k, which is the number of memory accesses, and wkt, the working set of a process at time t. Okay, so as you increase the number of memory accesses k, over time you would find that at a certain value of k, the working set wkt would saturate. Most programs would represent this behavior. There may be some programs that may represent pathological behavior by having a non-constant working set, but most programs would have a stable working set. If we can identify this working set accurately, then we have a pretty good page replacement algorithm. Let's look at how you can implement the working set page replacement algorithm. The working set page replacement algorithm works by evicting a page which is not in the working set of the process. We have the algorithm which periodically scans all the memory pages. Every so often, all the pages in the main memory would be scanned. With every page, there is a referenced bit that is marked by the hardware. So in every scan, these bits would be examined, and at the end of the scan, these bits would be reset. So between two scans by the algorithm, some pages would be accessed, some may not be accessed. The pages that are accessed, their reference bits would be set to 1 by the hardware. The pages which are not accessed, their reference bit would be 0. So the algorithm works as follows. It would examine the reference bit for each page. If the reference bit is 1, then it would set the time of last use for this page. So by time of last use, we refer to a virtual time. The virtual time increments upon every scan. Every scan by the algorithm through all the pages, it represents one tick in the current virtual time. So if R is 1, then we set the time of last use to the current virtual time. If R is 0, which means that the page was not accessed during the last tick, and the age of the page is greater than a certain threshold, so we set a threshold tau. This threshold could be any value that the operating system designer thinks that's useful. So if the age of the page is greater than a certain value, then we remove this page from the system. We evict the page. If the reference bit was 0 but the age is less than the threshold, then we remember what was the smallest age for the page, and we remember the page itself. So finally, if we scan through all the pages and we find that there is no page whose reference bit was 0 and whose age was greater than the threshold, Then we evict the page with the smallest age that we had identified during our scan. So the algorithm is pretty straightforward. We examine every page. If the reference bit is set, then we set the time of use to the current virtual time. If not, we examine if it's older than the threshold or younger than the threshold. If it's older than the threshold, then the page would certainly be evicted. If not, it may be evicted depending upon whether it has the smallest age. All right. So the working set essentially is determined by the threshold tau. The larger the threshold, the larger is the window during which the working set is tracked. So, and presumably more accurate the algorithm would become. So at the same time, if you have a very large threshold, then you will need more bits for the current virtual time to keep track of the time. So the size of the threshold is really limited by the number of bits we dedicate to record the current virtual time. Finally, we will look at certain design issues for paging systems that you may encounter when designing any page replacement algorithm. So first issue is whether the page replacement policy is global or local with respect to a process. So what we mean by that is, let's say we have three processes A, B, and C. So figure A shows the original allocation of memory pages for these processes. So in figure B, we have a local page replacement strategy, and in figure C, we have a global page replacement strategy. By local page replacement, we mean that if process A has a page fault and a victim has to be selected, then one of the pages of process A would be selected as victim. You won't select a page from process B or process C. So in this example, A6 is selected because that's the most eligible. A5 is selected as victim and A6 is brought in because that was the most eligible. A5 was the most eligible victim page among all the pages for process A. On the other hand, for global replacement, you would look at all the pages of all the processes. You don't make a distinction which process a page belongs to. So in this example, page B3 was the most eligible process page to be evicted. So um, so A6 is brought in and B3 is evicted. So basically for local replacement, you would look only at the process which caused the page fault, whereas for global page replacement, you would look at pages of all the processes irrespective of who caused the page fault. So global replacement is more efficient, whereas local replacement is, you can say, it's more fair. Another issue is internal fragmentation and external fragmentation. Fragmentation usually refers to the wastage of memory in some or the other form. So internal fragmentation occurs if you allocate a certain amount of memory to a process and the process doesn't use all that memory. So essentially the allocated memory would be wasted if the process doesn't use all of it. So a common example we already discussed is that let's say process is allocated a 4 kilobyte page, but it uses, let's say, only 1 byte of the page. So rest of the 4 kilobyte page is wasted. This is known as internal fragmentation. The wastage is internal to the allocated memory for a process. On the other hand, you have something called external fragmentation. External fragmentation occurs when you have free memory all over the system, but none of that memory is usable. By that we mean that, let's say a process needs a large amount of contiguous memory, that is memory locations that are next to each other. So in this example, in the figure, a process wants 16 kilobytes of contiguous memory, which means it needs, let's say, 4 pages of contiguous memory. However, all the free memory is broken up into really small parts. So there are two 8 kilobyte free memory locations, and there are two 4 kilobyte free memory locations, but none of them are next to each other. So there is no single 16 kilobyte contiguous memory location that's free. So we cannot satisfy this memory allocation request because there is no contiguous 16 kilobyte memory location. So this is an example of external fragmentation where there is enough free memory, but it's not all together to satisfy a memory request, to satisfy an allocation request. Um, so, so both internal and external fragmentation are possible. In virtual memory paging system, if you have all the pages of the same size, then internal fragmentation can certainly occur. If you have very large pages, then there is more internal fragmentation. If you have small pages, there is less internal fragmentation. Um, External fragmentation usually will not occur unless you have a need for contiguous pages. If you ask for, let's say, 16 kilobytes of memory, but you don't care if the pages are next to each other, then there's no problem. We could have allocated two 8 kilobyte chunks from different locations in memory, or one 8 kilobyte and two 4 kilobyte um, chunks from different locations. So the external fragmentation is a problem in paging based systems only when we want the allocated memory to be contiguous. So page size, determining the page size, we talked about it already in the previous lecture. If you have large page sizes, then you may have more internal fragmentation, but then your page table sizes may be smaller. Conversely, if you have small page sizes, you have less internal fragmentation, but you may end up with large page tables. Um, so operating systems usually don't wait till a page fault occurs before they select a victim page. When a page fault occurs, a key priority for operating systems is that they need to quickly resolve the page fault. If the page fault requires the allocation of a new memory page, then they want to quickly find the page. They don't want to wait till a victim page is evicted and then only allocate the page. So, so the strategy around this is that um, you would the operating system would evict pages ahead of time. It would anticipate that memory is needed very soon, so they would evict certain old pages ahead of time. There's usually a process, a special process called a page daemon, or sometimes it's also called a swap daemon. And you can check in a Linux operating system. If you'll check the list of processes, you may find a process called kswapd or kernel swap daemon. So the purpose of the swap daemon is to run periodically and to examine all the memory pages and identify potential victim pages, and to basically free up memory. So when do you evict memory? If the system doesn't have memory pressure, or if, let's say, the system has lots of free memory, then there is no need to evict anybody, right? Only time we want to evict some page is when the system is under memory pressure, which means that the memory utilization is very high. Usually the operating systems maintain two thresholds. These thresholds are also called watermarks. There is a low threshold and a high threshold, a low watermark and a high watermark. So the way the eviction policy would work is that the memory utilization would be monitored. Let's say the memory utilization goes above the high watermark. We could, for example, the high water mark could be 90% of memory usage. So if the total memory usage goes about 90% of total memory, then you have hit the high water mark. At that point, the eviction algorithm would kick in. It would start evicting pages till the memory usage falls below the low water mark. So again, maybe the low water mark is 70% of memory usage. So eviction algorithm would start when the memory utilization hits 90%. It would continue until the memory usage falls below 70%. So why do we have two thresholds, two watermarks? To basically to implement something called a hysteresis. What this means is that you know, if you have only one threshold, then you might evict just enough pages to fall below the single threshold, but soon enough the system would jump back above that single threshold. So you will have a situation system which constantly oscillates back and forth around a single threshold, and that's not good for system performance. Uh, so usually for more predictability, system will have two thresholds, a high water mark and a low water mark. So once you hit the high water mark, you get the system below the low water mark, and then it takes a while for the system to hit the high water mark again. So that way the system performance is more predictable rather than oscillatory. Finally, there is a problem of thrashing. Thrashing occurs when the working set of all the processes in the memory is greater than the sum of the total memory available. For example, your computer may have only 4 gigabytes of memory, but the total working set of all the processes may be 10 gigabytes, right? So whatever page replacement algorithm you use, it's not going to work because the working set of all the processes may never be satisfied. So in such cases, what happens is that the operating system would be constantly writing pages to the disk and reading pages back in, and then writing the same pages back to the disk and reading the back end. So it's essentially doing a lot of input and output and not doing any useful work. So in such cases, the system is said to be thrashing, which means it's basically doing page in, page out. So the only way out of thrashing is to reduce the degree of multiprogramming. What this means in simple words is to reduce the number of processes that are being handled by the operating system. Some operating systems would just randomly kill some processes. Linux, for example, used to do this till at least a few years ago, where if the system starts thrashing, it would just randomly kill a process that it thinks it's not very important, which is kind of annoying for users, but it kept the machine running, right? Um, on the other hand, you could also resort to a technique we learned earlier called swapping. In swapping, you would take an entire process and kick it out to the disk. So that way freeing up the memory. So the process won't be running, but it would basically be sitting on the disk waiting for the memory pressure to go down. So so that way you can reduce the number of processes that are competing for main memory, and bring it to a sane value where paging operations can have a meaningful effect. So this brings us to the end of discussion for page replacement algorithms.